Right. So what else we had? PV is the one that we proved yesterday, the long one. PV is equal to a third mn mean squared, right? And then I know I didn't give you this version, right? But if I carry across volume here, right? What is mass and volume? Density. So you could also write P is equal to 1/3 density n mean squared. Right? Then we proved this as well. Kinetic energy is equal to what is 3 on 2 kT. Any more? No? Okay. So today we're going on something called thermodynamics, right? Thermodynamics basically, I'm gonna give you a little intro on how it works, right? Thermodynamics basically works like this. Right? If I give you a gas and the gas inside here, the gas has internal energy, right? What is the symbol for internal energy again, Pete? What was the symbol for internal energy? U, right? So, Pete, how can I change this internal energy? The internal energy for gas, ideal gas, is purely what? Purely kinetic. Very good. So, how can I change that internal energy? There are two main things I can do here on. What are they? I want to change the internal energy. What are two things I can do? What we can do? Think about it. We can heat it, so we can apply heat to the system, right? So number one, we can apply heat to the system. What else we can do? Anybody? I want to increase the internal energy in there. Number one is heat it. Number two is what? And you'll kind of set the answer when we are doing internal energy. You can do work on, very good. You can do work on the system, right? This is work done on the system. Correct? Work done on means that I am going to compress it. You're doing work on it. Right? It can also have work done by the gas, which means that the gas is going to cause expansion. But what will expansion do? Expansion will give it more space and allow it to lose energy. So it will drop the internal energy. So what you just do, right, is that you just represent work done by with a negative sign because it's going to reduce the internal energy. Right? What you see in there is the first law of thermodynamics. Right? This is the first law of thermodynamics. Right? All you have to think about is how to how to affect the internal energy. Right? So that is your first law of thermodynamics, and we're going to learn to apply it. Right? I want to find a way to link everything, right? You all remember what work done? Work done is what? Power by time or force by distance. Right? I want somebody just take a minute, right? Take a minute and see if you can force by distance, right? That's work done, right? See if you can find a way to bring in like pressure and volume and thing into this work done formula. See if you can do that. I'm just giving you a minute to win. See if you can bring in pressure into that. Right? You have to remember things from before, right? The one force and distance anymore. See if you can bring in pressure and volume. Just one substitution happen. Yeah, anything else? Yeah, you way down in the back there. Yes, please. Yeah, yeah, anybody? Should I anybody? Right? I'm gonna give you a hint. Yep, forces pressure by area. Somebody really handle it. Right? Pressure is equal to, right? Work done, right? Remember, force is pressure by pressure is force on area. So force is pressure by area. Right? And area by distance is generally your right? Area by distance is generally your volume. Right? If you have the area of something by the height of the line, that's your volume. Right? So basically, that just means change, right? So what we observe here is that the work done on or by is the pressure exerted by the change in volume. Okay? All right, so you can add that to your list. You can add it here, change in internal energy is Q by work done, and work done, right? Work done is pressure by change in volume. Well, change in work, right? That's symbol there, change. Let's go to the notes now and let's run through some of this, right? You'll understand the gist behind thermodynamics. Soraya, come on, what's your understanding it? Right? But of course, thermodynamics does not have to start with Q, right? They could rearrange the formula and start with Q. Some books have Q. So instead of U is equal to Q minus W, some of them have Q is equal to delta U plus W. Same concept, right? But they will define which W you're using. If it's work done on or work done by. That's okay. Let's take a look at the notes now on thermodynamics before we start anything, right? Right, those who want to do thermodynamics, that's one of the hardest courses in engineering. But you'll have fun. These future. Right, let's start here. First law of thermodynamics. Oh, I gave you this last slide, right? Right. First law of thermodynamics, right? Here we have two containers with the same gas, and it shows an expansion, right? Left to right, there's an expansion of the gas. Okay. So if the container with the gas is tightly fitted with a piston that is free to move, then the gas can be allowed to expand or compress easily. The internal energy is the sum of the kinetic energies of the molecules in the gas. Right? Remember, internal energy is kinetic plus potential. Right? But in an ideal gas, it's purely water, right? In an ideal gas, it's purely what? Purely kinetic. Right? If heat energy is right, if heat energy is added to the system as a gas, then its internal energy will increase. Also, if work is done on the system by compressing it, this too will increase the internal energy. This basically summarizes the first law of thermodynamics as this. All right. Please remember you have to define which W you're using. Right? If it's a plus, it's work done on. If it's a minus, it's work done by. Just see that? Don't forget that, right? Work is done by the gas. This is negative since if work is done by the gas causing it to expand, then this will reduce the internal energy of the gas. Right? The table below gives an idea of the signs, right? So watch this here. Let's focus on the first rule. Right? This technically sitting on the formula, right? But I put it in a table form kind of help. Right? Right. So the internal energy is the change in delta U change in internal energy, right? If the temperature increases, then delta U is positive. Right? So what is saying here is that if the temperature increases, the delta U is positive. If the temperature decreases, the delta U is negative. If there is temperature constant, that means temperature not changing, then the delta U is zero. That's okay. So technically, Kaylin, what is delta U dependent on? No, ma'am. Look at that column there. Delta U is dependent on its temperature. Can't pay attention, ma'am. Huh? You wasn't reading that. Right? Q is the heat energy. Q is the heat energy. If heat enters the gas, positive. If heat exits, negative. If there's no heat exchange, zero. Diane, that makes sense? Second column there. And it makes sense for sure. That makes sense? Huh? And W. Work done on the gas is positive if compressed, negative if it expands, and if the volume is constant, it's zero. Right? Look at the formula that we proved there. And we said that work done was pressure by change in volume. If the volume not changing, then the work done is what, Jacob? Oh, work done is pressure by change in volume, but the volume not changing, but constant. Work done is what? All right. Nice, good. Here's an example of different types of compression. You have adiabatic, isothermal, isobaric, right? Normally I'll give you this to home. But I kind of more home to give you, right? So we'll see also next week. Right? Isothermal basically means that you keep your temperature constant. Right? If you keep temperature constant, right? Anybody remember what is zero? Just said it. Selena, you remember what is zero? If you keep temperature constant. Remember what is zero? U W Q. U was zero, right? Isobaric means constant pressure, and adiabatic is where you keep manipulating both pressure and volume. Okay? Now, we gotta get rid of the whole. So if you see those words, you know what I mean, right? All right. Right. Before we start doing questions, remember, work done, as I showed you a little while ago, if you do the little proof I showed you, work done is force by distance, force is pressure by area. So work done is this nice little formula here. Pressure by change in volume. Are you okay with that? Right? Last thing before you start doing out. But that yeah. Last thing before we start doing out there, right? Watch here. If I give you a pressure versus volume graph, right? If I give you a pressure versus volume graph, the area under the graph is moved done. Right? Just to know one table and write that down because you will need that just now. If you have a pressure versus volume graph, the area under the graph is your work done. Right? If I give you the find the area, right? No integration, just they'll give you a rectangle or something or square. Right? I have a question here. Suppose I give you a graph like this. Actually, during this graph, there's constant volume. How do I draw that? I want to draw a graph of pressure versus volume, right? But the volume constant. How to draw that? On the graph. You must necessarily me. What's the answer? You know to come in. How to draw that volume on the graph? This graph showing you that pressure staying constant, right? But the volume changing. So my question is, pressure changing, but the volume constant. How vertical line? Remember all lines are straight down, right? So vertical line is better. Right? What's the area then? What's the area under that graph? I know area, right? So what I mean now, here. I know area. So what does that mean? Yeah, we said already. But what does it mean? Done, right? No work done. Okay, that's what happened there. No work done. Anyway, right? Hi John, are you okay there? Katrina. So when the volume constant, no work done. Yeah, you're okay, nice. Right? Things to note. If the volume of the gas is increasing, then the work done on the gas is negative. But if the work done by the gas is positive, right? That makes sense? If the volume increasing and the gas expanding, so that's work done by the gas. But the volume decreasing, the gas is being compressed, right? So that's work done on the gas, right? If the volume of the gas, constant, then the work done is zero. Right? You know what's already, right? Will you give it up? All right. I want to start question, but I want to show you this too because question is come for this as well. Are you okay? Let you all just take in there. Take a minute, right? That's a minute here. Talk to your friends. Right? And then we're gonna take a look at molar heat capacity. You remember specific heat capacity? Yeah. Now we're gonna take a look at molar heat capacity. So instead of specific, it's now molar. Right? This is the last theory. I want to make sure you understand this so that we can try some questions, right? Right. All right, let's go now. Right, so we need to learn about this new quantity called molar heat capacity, right? You all would have done something called specific heat capacity. right? But now we're not interested in mass, we're interested in moles, right? So we're looking at something called molar heat capacity. Same thing, right? Same concept, right? Same concept. That's all. Take a look at the hand out there. That's it. Pull. No, I want right? So we're gonna take a look at molar heat capacity. No, intercontinental. I know I'm not used to choosing that right now. That's when you went out champions. We are playing. All right, so what is molar heat capacity, right? When energy is supplied, right, and the energy causes temperature change, molar heat capacity is NC delta theta. Same concept, right? But we are going to focus on two things. We are going to focus on the molar heat capacity at constant pressure, and we are going to focus on at constant volume. Huh? Sorry? Huh? No. This was the one that you all know. This is for specific heat capacity, but we're looking at moles. N is moles, right? Just to help you remember, right? This was from long ago, right? We focus on this now. So, what is molar heat capacity at constant pressure? Molar heat capacity at constant pressure is Cp, and it's Q over N delta theta. Remember, Q is heat supply, right? And at constant volume, Cv is equal to Q N delta theta. You all okay with this? Right? So we're only considering molar heat capacity under two conditions. Constant pressure, constant volume. That's all. Right? We're not interested in no other condition. Yeah? Lowercase c. It's not, it's molar heat capacity. Lowercase c. Not watching anything about what you know. All right. So there is a nice relationship between two of them that we're going to work out now. Ready? That's not sorry, right? Ready? Right, so watch this here. So there's a nice relationship that comes out of all of this, right? So watch this here. Let's start with the easier one. At constant volume, we know that Q is equal to, I just rearranging this, right? N CV delta theta. At constant, do you only remember the formula? Remember this here? I just want to rearrange this, right? I'm using U is equal to Q minus W. I'm doing work done on. Right? So W is equal to U plus Q. Sorry. Q is equal to U plus W. I'm using this, right? So watch this here. Q is equal to U plus W. But what do we know at constant volume? At constant volume, what do we know about work done? So at constant volume, we know that work done is 0. So it means that internal energy is NCV delta theta. That makes sense? Aaron, you're looking like a girl off there. Okay, remember this? Q is equal to U plus V and U plus W. W is 0, right? W is 0. So we know that U is equal to this, right? What I'm doing here, I'm trying to link these two here till here. Right? I'm trying to link these two here. Right? If I make Q the subject of the formula here, Q is equal to, let me know which one here. Q is equal to NCP delta theta. Right? Q is equal to NCP delta theta, right? And we know that Q is what? Q is U plus W. That's okay? At constant pressure, do we have work done? Yeah, constant pressure. Remember this? And we have work done here at constant pressure, pressure versus volume. And we have work done, right? So we have work done and we have internal energy. Can I? So I'll leave it like that. Can I bring this up here now? Yeah? Can I substitute U? So if I substitute U in here, let's call this equation 1. Let's call this equation 2. Substitute U in equation 1. Watch what will happen, right? I'll get NCV delta theta. So I'm taking off this and I'm writing this. Plus W is equal to NCP delta theta. Right? All right. Watch here. Let me show you understand, right? All right. 3 more lines and we're done. Are you okay with this? Up to here? Right. What do we know work done is? Work done is pressure by change in volume. Correct? But what is here? What is P by V again? Up there. You'll see that? Since P by change in V is equal to N R, so if the volume changes, more than likely the temperature will change. So P by change in V is equal to NR by change in temperature. You okay with that? So now I could take off W and write this. Right? So I'm going to take off W. And I'm going to write NR change in temperature. You see that? So I take off W. W is this and this is this. So I just make these two equal. Yeah? Kalina? Right? So I replace W with this equal to NCP, that's theta. Right? What do they all have in common? They all have N and delta theta. You see enough? So now I can cancel it off. So I'll get C plus R is CP. That should be V. You see enough? If I divide out all of this, I'll get C plus R is CP. So it means that I bring it across, it means that CP minus CV is R. Right? So it also means that CP is always bigger than CV. So molar heat capacity at constant pressure is larger than molar heat capacity at constant volume. Okay? And well, you might see it here because more energy is required at constant pressure than at constant volume. Right? Again, the next proof that you have to be able to do. Okay? All right. So this whole thing here is just to show the relationship. That's it. You're good to go. Q is equal to NCP delta theta. Q is equal to NCV delta theta. And CP minus CV is R. Right? I like this too. Sometimes we don't see this. Right? So you can add that. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 formulas. Right? Now we're gonna practice a couple of questions on this. The purpose of that whole proof that you're writing there is really to show the relationship between CP and CB. And we learned that CP is much larger than CP, right? The difference is R. What's R again? The R was the molar gas constant, right? 8.31, right? Get quiet, boy. No marquis. Show marquis and pay attention. Huh? Marquis. Like pay attention.
Yeah.
Nice, Marquis. Next question come up with for you, right?
No, Chano, yeah. It's a finish. Wait a second, we have a question.
What?
We have a question, too.
Yeah, you got question as well.
Okay.
Yeah. Yeah, really. Wait, I love one. Wait, think about it.
No, I didn't think of that. I didn't think about it. I didn't think of it.
Oh, right.
Wait a minute. Wait, the one next one?
Yeah. All right, let's go. All right, so the first thing you want to look at, you want to look at the question, right? You want to see everything. All right, let's start here. Let's start here. Figure 4 shows the routine of CMD. You can screenshot the whole thing if you want to. Take a picture out, go through it part by part. Okay, good. Are you ready? No, we can't do it. You'll have a question, right? Alright. So let's take a look at it together. So first thing you do, you write down all the important stuff. Figure 4 shows the gas containing a cylinder in thermal equilibrium at a temperature. So they gave you T. So first thing you do, you write down T. T is 315 Kelvin. It's thermally isolated, so no heat going to be added to the system. Its initial volume, so they give you a V 2.9 by 10 to the minus 4. Everyone on here. Yeah, that's like, all right, that's all the market things. Right, and the pressure. All right. So they're online. We got disconnected, right? So I just try back up. Let's try back to. Right, let's just catch back up here. Right. So they gave us temperature, volume, and pressure, and they asked us to state the ideal gas and find the moles, right? So we're using PV is equal. Wait, are disconnected? Or connect or still on YouTube, right? So PV is equal to nRT, right? PV is equal to nRT. So N is equal to PV over RT. Right? Pressure is equal to 1.03 by 10 to the 5. The volume is equal to 2.9 by 10 to the minus 4. R is 8.31. And the temperature in Kelvin, so we got to go. How much you got? The number of moles. 114. Anybody else got that?
Yeah.
Yeah. Right. Here's what they want now. They said that the gas is then compressed to 3.5, right? Means that they compress the gas, to the volume smaller. Right? They compress the gas so the volume is smaller. Everybody okay with that? But here what happened? The temperature rise to 790. Explain on a microscopic, a macro. Macro is where you use the first law of thermodynamics. Micro is where you use it in theory. Right? So think about it, and then I'm going to ask somebody to explain it to me, right? The name of S, I'll be calling them. Whenever you are calling you. Think about it, right? How does the first law of thermodynamics explain this rise in temperature? And then how does it connect? Let's do the easy one, kinetic theory, Vanessa. How does kinetic theory explain this? Why did I why did that compression increase the temperature? What? Yeah, Vanessa. In terms of kinetic theory, the way the particles behave. Real simple, they compress the gas. What's happening? They compress the gas. What's happening to the particles? Yeah. And because they collide more, right?
Yeah.
Right? And if they collide more, pressure will go up. And if pressure goes up, temperature goes up. That's okay? That's on a microscopic scale. But the macro is the one I want to hear now. Right? Yeah, put up your head. We run out for it more. Now, right? So you want to get in macro. Yes? Try that. The macro a little bit harder. Take your time. Right? Remember, you compress the gas. So see what compression going to do. And in terms of the formula, everything must happen along the thermodynamics formula. I don't mind if it happens to you pure, but you want to finish it off. Huh? Okay, so compression means what? The volume will work itself on, right? So if work is done on the gas, what would happen? The internal energy will increase, excellent. And if the internal energy increase, what will happen? Look at the last part, you're almost there. You're almost there. Look at the last part. If the internal energy increase, what will happen? It will rise, increase temperature. You all remember when we went to the table, we said that temperature was directly linked to internal energy. Remember that? You should remember that, right? Wait. So write this here from my right. Write this here. First one, I give you the macro. In macroscopic scale explanation. Since the gas is compressed, since the gas is compressed, then work is done on the gas. Then work is done on the gas. So this implies that the internal energy of the gas will increase. This implies that the internal energy of the gas will increase. And since internal energy is directly proportional to temperature, and since internal energy is directly proportional to temperature, then an increase in internal will give an increase in temperature. An increase in internal will give an increase. An increase in temperature will give you an increase in, or increase in internal energy will give you an increase in temperature. All right. So if you look at the years after that, they asked some macroscopic explanation, but they didn't carry it along and say use the first law. All right. So I want you to learn that, please. Whenever they say macroscopic, they want you to use the formula of thermodynamics. Whenever they say microscopic, that's kinetic material particles. Okay? Because the other years they asked for an explanation, but they didn't carry it along, which what they use, right? And part 2 should be easy, right? Part 2 is using kinetic theory. Less space means the particles will collide more, and increase in collision means an increase in temperature. Sorry, an increase in pressure, which means an increase in temperature. Right? Less space, more collisions, greater pressure, greater temperature. Right, move on now, finding pressure after compression. Finding pressure after compression. Jacob, will the number of moles change? After compression, will the number of moles change? Only find something yeah. Yeah. Huh? Yeah, so box, yeah, right, correct. Right, number of moles will not change. Very good. Go ahead. Finding pressure, knowing that number of moles does not change. Actually, until you back here, I don't see it. Until you. Click on your look at the this is come back in the class. Nah, oh yeah, still yeah. Somewhere you didn't come back. By the way, the pressure is more or less. Yeah, well, what if I'm not using again here? What's here? Same thing. Same thing, right? PV is equal to NR. What number hold 0.011 something? 0.0114. Right, by R is 8.31. By temperature, what's temperature now? 790. All over volume. The volume is 3.5 by 10 to the minus 5. What is that? 2.14 times. Right, so you see that the pressure went up, right? So the pressure went up. So the pressure is now 2.14 by 10 to the 6 Pascal. Are you okay with that? Next part, Susanna. I clicked on you, that's all right. What time coming up there, Susanna? Try part D for now. Work done on the gas, so write it down one time. Work done on the gas is 90 joules. Right, so write down work done on the gas is 90 joules. Using the first law of thermodynamics, find the increase in internal energy of the gas. 1 mark. One mark. You have to remember something that we did in the table. Right? So go back to the handout if you want. There was something that we did in the table that will help you work this out. Right? Check back in the table and tell me which formula I think we're going to use, and then there's something you have to remember. Sorry, sir? Yeah, you really. Why don't I put offside? Take it off. Right? What's the formula we use in MSc to pick on Atelier? What's the formula we use in part D? Oh gosh, man. Yeah, Atelier. What's the formula you're going to use here to help you find internal energy? U is equal to what? Yeah. Which one? Read the question, good. It's in there. They told you what to use. Use what? Olha. Que é o site fala então. Essa boca era para não deve ter. Yeah, I tell you which formula is that? You can tell motion on the board. Because one on the board we use it. Then I get alpha. Question tell you what to use in part D. Use the right first law, right? So which one is that? Use equal to which one there is the first law of thermodynamics? Right? Q plus work done, right? Q plus W. Nice. They told us that the work done on the gas is they told us that the work done is 90. Anybody know what Q? I want to point out something here for you.
Tell them to pass through your classroom.
Yeah, tell them something coming up right now.
But it really seems to you.
Yes, lock the doors down, leave them inside it. Yeah, sorry. Where's Q? What's don't say it don't matter. Because it's what? Because Q is 0, right? Watch why. If we go back to the table, right? And when heat is not added, Q is 0. Remember that? Look at the part in black. Thermally isolated means no heat is going to be lost or no heat is going to be supplied to the surroundings. That's okay? That's the reason why Q is 0. Alright? So Q is equal to 0. So therefore, U is equal to 90 joules. That's okay? So you have to remember that, right? Write down that Q is equal to 0 because the system is thermally isolated. Then try the last one. The molar heat capacity in the glass container. Find the molar heat capacity in the glass container. 1,400. Try to find the last part. Right? Go ahead and solve this code. Right? So which version are we going to use here? Which of these formulas we're going to use here? Which one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11? 10? Wrong. 10 is here. Using 11. No, we can't use 9 because Q is 0. Right? So we have to use Q. Right? So we're going to use the last formula. We're going to use U is equal to N CV delta theta. So therefore CV is equal to U over N delta theta. U is 90, U was 90, N was 0.0114, and the temperature change at the rate number. What's the temperature change again? You gotta go back and get it two temperatures. One was 790. 790 and 4. Oh, 72 values. And 3. So minus them and you'll get CV. Well, divide them and you'll get CV. Very confused on any part? Anybody confused on any part? I'll tell you. You okay with everything? Sure. Work out CV from up. Let's see what you got. Online, you're okay with these values? Yeah. What will you get? 16.6.
No.
16.6, remember it's joules. Joules per mole per Kelvin, right? Let's go again. Let's go again, right? Everybody okay with us? Right, so it's important to understand the quantity now what you're going to use, right? Let's try one with a little graph now. We'll set a graph after if we have time, right? Try this one here. You'll see everything. Try that this. Try that here. Take your time from doing by yourself, pass on, take a look at it, right? So, Ready yet? Write down what the values they give you, right? So the 6.2, write down what that is. They give you a CP, write down every single thing, right? Write down the temperature change. Do your thing. Right, the first part you can leave it out if you want, right? The first part is the steady law and what everything means, right? You can leave it out if you want. But that's looking again, right? But, you know. Here, no works here. Oh, you are. Till the pass around, take a look, yes. We'll see what they have. Online, when they finish, get sign a value. The time, right? So far, you can reach. Right, they ask the thermal energy in the first one, right? So which formula are you using there? At constant volume. Where are you using there? First one. The tenth. Yeah. Right, you're using the ninth one there, constant volume, right? Right, Q is equal to NCV W. What happened? That's constant volume again, Ruben? Huh? What's that zero? Work done is zero. Remember that, right? Work done is zero at constant volume. That'll help you in part B. How much you all got? Right, so 1937.5 joules.
Yeah.
Yeah, nice. How much internal energy, right, so we know that internal energy is what? Internal energy is energy supplied by work done, right? But if the work done is zero, Saraya, then the internal energy is purely what? If the work done is zero, then U is purely dependent on what? The what? Q, right? And we know that Q is 19.75. Right, so your final answer is 1937.5 joules. Everybody okay with that? Yeah, and then if you follow y is y delta U is delta W is 0, right? Yeah, Aaron? So Aaron, here what happened now, right? So if instead the gas was heated at constant pressure, so the gas is heated now at constant pressure, that's now CP, right? From 25 to 50, the thermal energy, what is that? Q, W, or U? Thermal energy. What is that? Which letter, Aaron? Q, W, or U? That'll Q, nice. Right? So we know that Q is equal to 3200 joules. How much work is done by the gas in this case? You have to subtract 3200. Why? I ain't saying it wrong. But why? Work is done by the gas, eh? You're saying that? Work is done by the gas. So what's the relationship we're going to use here to Kaylin? Q is equal to U. No. You want to write the other way around. You want to write U is equal to Q minus W. Okay? Because remember, when I made Q the subject of the formula there, it was already work done by. Right? So U is equal to Q minus W, or W is equal to Q minus U. Right? So that was very good. That was very good error. Are you okay with that? Why are we doing that? Okay, so it's important that, of course, you had to learn those 11 formulas, right? Are you okay with that? How much is that? 1, 2, 6.5. Right, very good. Last one. Deduce the value of CP. Don't overthink it, it's really easy. Deduce the value of CP. If you get it right, we'll stop here. Wait, I have to call somebody. Wait. If you get it right, we stop here. No more. Faith was the easy way to find CP. All right, anyway, Faith, I'm opening it up. Anyway to find CP, you tell me. Take your time. What's your board? Oh, yeah. Which formula? As we got here. I don't know. You tell me. You tell me. Man, I don't get you if it doesn't tell me. Right? But that's the long way. That means they want class to go long. Anybody want class to go short? You have a shorter way. Yeah, Vanessa, since they want class to finish. Very good. 10 formula. 10 formula. CP is equal to R plus CB. That's all. Okay, and you have CB on top. You have CB on top. Next time, please. Don't give up, please. Right, everybody have decided, please? But you work it out, like that.
Okay.
Do your thing. What's your use of Q? I didn't say no wrong, but what's your use of Q? The high pressure. If you're using CP is equal to Q on N the theta. Huh? 3 to 1. Yeah, that is good. 3200 and it divided by N and temperature change. Okay? So that's very good. Right, because we'll get that right, we can wrap up after this one. Alright, Vanessa, you need to. 6.2 multiplied by what? That's not, I'm just checking this next method here. What's your guts? 20. Okay. Yeah, put them give me the 15. Alright, 9 job volume. Alright, online. That is it. That's it for today. Pure math people, we have a longer break. Right, you'll start at physics, you all can log out. Enjoy the rest of the education on 15 and 5 YouTube. Pure math people who don't follow a little bit, right? I'll have a long break. Not ready? Put the rest of them outside. Yeah. Walk down High Street. Figure out. Did I do any tricks multiple choice? That'll be a test. Trick multiple. Yeah, trick multiple choice. That'll be a test. We'll do that. So we online. Right? So let's take a look at this, right? Online you can message your answer. What's the minimum value there? But again. See? Right? So basically you have to find R, which is the square root of 8 squared plus 5 squared. That's the square root of 64 plus 25, that's 89. Right? They want the minimum value, so it's minus R. Right? So the first one there is C. Selena, you have to do right? The number 18 is C. $22. What is 22? Oh no.